Uh, Hello, everyone. Today I am going to talk about resource-aware protocols for network cost-sharing games, which is a joint work with Christodoulou, Vasilis Gkatzelis, and Alkmini Sgouritsa. At first, let me pictorially introduce the problem to you. In a cost-sharing game, we have a graph and a set of players, each having a source and a sink that she wants to connect through the graph. Players might have several options to connect their source to their sink. For instance, here, the red player can either use the UT edge or the UVT pad to connect U to T. In addition, each edge is assigned a cost function that determines the cost of using that edge based on the number of the players having it in their paths. This cost must be shared among the players using that edge. For example, here, if players choose their paths like this, each of them must pay the whole cost of the edges in which she is alone, and the blue and the green player must share the cost of the VT edge for load 2. That is where the cost-sharing protocol becomes important. A cost-sharing protocol determines how to share the cost of an edge among all the players using that edge. For instance, here, if we use the equal cost-sharing policy in which the cost of each edge is shared equally among the players using that edge, players will be charged 12, 23, and 15. In cost-sharing games, we assume that players act rationally, and each of them tries to minimize her share of the total cost. In this game, you can check that this strategy profile is an equilibrium, since no one can pay less by changing her strategy. The total cost of this equilibrium is 50. However, if we try to find the optimal strategy profile in sense of the total cost, we can see that the strategy profile in which the blue and the green player use the SUT path and the red player uses the UT edge is the optimal strategy profile. In this case, the cost shares change to 13, 13, and 5, and the total cost becomes 31. As you can see, the selfish behavior of the players led to a non-optimal equilibrium with high social cost. The question and the goal of this work is to see if it's possible to design protocols that yield equilibria with low social cost. Now that you have a general idea about the problem, let us get into some details. Formally, an instance of a cost-sharing game consists of a graph G and set N of players, where each player needs to connect her source to her sink. Each edge has a cost depending on the number of the players using it. We assume that these cost functions are non-decreasing, and cost of the edge that nobody uses is 0. Each player's set of strategies are all the paths in G that connect her source to her sink. Strategies of all the players form a strategy profile that we denote by S. As I said, our goal here is to design cost-sharing protocols to determine the payment of each player in each edge regarding the strategy profile S. We show the payment of player I in edge E by xi sub IE of S. There are some characteristics that we are going to consider designing the protocols. First, we need our protocol to be stable, which means it should yield at least one equilibrium in every instance of the game. Secondly, as I said, our goal is to design efficient protocols, which means we need our protocol to yield equilibria with low social cost. In addition, a protocol can be budget balanced or use overcharging. In a budget balance protocol, the sum of the payments of the players using some edge must add up exactly to the total cost of that edge for that load. However, we might have more power in designing protocols if we do not restrict our protocol to be budget balanced and add some overcharging to cost functions. In order to use overcharging, we define a new cost function on each edge, which is greater than or equal to the original cost share, and we share these new costs among the players in our protocol. Using overcharging is some sort of a trade-off. It gives us the power to design more efficient protocols, but on the other hand, it increases the total cost of the outcome, which might be not good for us. We define the total cost of an outcome of the game as sum of the costs of the edges. Here, L sub E of S is the number of players using E in a strategy profile S. To evaluate a protocol, we use the notion of price of anarchy. I think most of you are familiar with this, but to be complete, price of anarchy of a protocol over a class of games is defined as the supremum of the ratio of the cost of the worst equilibrium to the cost of the optimal solution among all game instances in that class. Note that in protocols with overcharging, we consider the ratio of the new total cost to the original optimal solution. Otherwise, we would be somehow cheating by changing the optimal solution with overcharging and have a better price of anarchy by that. Our goal here is to design protocols with low price of anarchy. But the question is, what power do we have in designing such protocols? Here we have three classes of protocols based on the informational power we have in defining Xi sub IE of S. There are protocols that use nothing but the set of players using the edge to share the cost of that edge among the players using it. We call these protocols oblivious. In the other extreme are protocols that have all the information about the graph and the players to determine the cost shares. We call this class omniscient protocol. In contrast to these two extremes comes the middle ground class of protocols that know everything about the graph, but nothing about the players who are not using this specific edge. We call such protocols resource-aware protocols. It's clear that we have more information in resource-aware protocols than in oblivious mode. But it's not clear how we should use this information to achieve better price of anarchy. In this paper, we use this extra information to design efficient resource-aware protocols. Designing a protocol that works for every instance of the cost-sharing game is not easy. So we design protocols for specific classes of games. We classify games in different aspects. One of them is the class of graphs that G belongs to. Here we consider two cases of series parallel graphs and directed acyclic graphs. Another classification is by the class of cost functions. In this work, we consider two classes of convex and concave cost functions. In addition, we classify our games based on the strategy set of the players. We call a game symmetric if all the players have the same source and the same sink, and we call a game multicast if players have the same sink but might have different sources. This is an outline of the results that we are going to talk about. As you can see, we consider several classes of cost-sharing games, and we have some positive and negative results around them. In some cases, we generalize some of the previous works, and for some cases, we propose entirely new protocol. This is a long literature on cost-sharing games. I don't have time to go over all of them, but the most related works are these four papers, where the first two started this line of work by considering omniscient and oblivious protocols in different classes of games. And the last two introduce resource-aware protocols and show the power of these protocols over omniscient one. Among these works, the first and the third one are restricted to constant cost functions, and the second and the last one are restricted to simple case of a scheduling game, which we can see as a cost-sharing game on parallel links. In this paper, we are going to combine the strength of these works by considering more general classes of cost functions for more general classes of graphs. Let us see what the contribution of this paper is. As I said, we consider several classes of cost-sharing games. At first, we generalized the protocol introduced for parallel links for to work for series parallel graphs. And we show that this generalization is stable, budget balanced, resource aware, and achieves price of anarchy of 1 for series parallel graphs with concave cost functions. After that, we design a protocol for a more general class of games, which is symmetric games on DAGs with concave cost functions. This is the main result of the paper. In order to design a protocol for this case, we are going to use overcharging in our protocol to reach a good price of anarchy. The first question that pops up in mind here is what the optimal strategy profile looks like. We proved that in an optimal solution for a symmetric game on DAGs, all the players use a single path from source to sink. We use this fact in designing the protocol. In fact, we design our protocol in a way that it forces all the players to be in this optimal path. After all, let us see the protocol that we propose for DAGs with concave cost functions. We name our protocol the Never Walk Alone protocol, as it charges players who are alone in some edges a high amount of cost. As I said, we are trying to force players to use the optimal path, but the protocol is meant to be resource aware. So in each edge, we know nothing about players that are present in the game but do not use this specific edge. So we don't know the total load, and we cannot determine the optimal solution. Therefore, instead of finding the optimal solution, we locally force players out of non-optimal edges. To do so, in each edge, we assume that there are no other players in the game. We look at the number of players present in that edge, and we find the optimal path for that load in the graph. We can do that since we know everything about the graph and the cost functions. Then we check if this edge is part of that optimal path. If not, we can conclude that the strategy profile is not the optimal solution. So we charge the players a high amount of cost and force them out of this edge. As I said, here we are able to find the optimal path for any load since we know everything about the graph. Note that this is the power of resource awareness, and it's not possible in oblivious protocols. And this is the point that we use the information, the extra information that we have in resource aware protocols. Another idea we use is to have an ordering pie over players and charge the highest priority player in each edge that we call the leader of that edge, a small amount which is in reverse proportion to cost share of other players in that edge. I am going to show how this helps us to have all players in the optimal path in the next slide. Now let's see the actual protocol. These were the ideas behind the protocol, but in the actual protocol, as I said, players other than the leader share the whole cost equally if the edge is not in the optimal path for that load, and each of them pays 2 times the total cost of that edge if that edge is not in the optimal path for that load. In addition, we define epsilon sub e in a way that the leader pays an extremely small cost that is in reverse proportion to the cost share of the other players. As you see here, we have a big amount of overcharging, but this just happens in non-optimal edges or in the case that we have only one player present in the game. So this overcharging does not make the protocol inefficient. In order to evaluate the efficiency of the protocol, I am going to prove that in the equilibrium, all the users follow the optimal path from S to T. To do so, first I prove that the highest priority player does not walk alone. This is due to the fact that she pays a very small cost in edges where she is not alone. Then we prove that there is no equilibrium in which players use different paths. There is no time to go into the details, but the idea is to consider the path that the highest priority player follows. She is not alone there. And since she pays a small amount, which is in reverse proportion to the payment of the other players, we can prove that either she has the incentive to deviate or one of the other players in that path. And after showing that all the players use the same path, We show if this path is not the optimal path, players have incentive to deviate. And this is due to the fact that we charge players in non-optimal edges a high amount of cost. At last, using these lemmas, we show that the never walk alone protocol yields a price of anarchy of 2 plus epsilon for DAGs with concave cost functions. And if we can assume that we have more than one player in the game, it yields price of anarchy of 1 plus epsilon. Another case that we are going to consider is the class of multicast games with concave cost functions. As you may recall, in a multicast game, players have the same sink, but might have different sources. For this case, we show that with resource-aware budget balance protocols, we cannot go beyond price of anarchy of n. And even with the use of overcharging, we cannot achieve price of anarchy better than a square root of n. Actually, the idea behind this proof is to make some counterexamples. As you can see, one of the counterexamples graph in this slide. And using these counterexamples, we show that it's not possible to have protocols with good price of anarchy. After considering all these classes of games for concave cost functions, we are going to talk about convex cost functions. Now we are going to talk about convex cost functions. For games with convex cost functions on series parallel graph, a simple protocol introduced by Mullen in 1999 works fine. This protocol assumes that players come one by one according to pi and charges each player in each edge as her marginal contribution to the cost of that edge. We proved that this simple protocol is stable, oblivious, and budget balanced and achieves price of anarchy of 1 for SPGs with convex cost functions. The question is, can we do the same for more general classes of graphs such as DAGs? Note that one of the difficulties that arises here is that the optimal solution does not have a simple structure like in the concave case. And the structure of the optimal solution might change entirely by a new player arriving. We proved that any stable budget balance and resource-aware protocol has price of anarchy of omega of n for DAGs with convex cost functions. And even with the use of overcharging, we cannot have protocols with price of anarchy of 1. We have the lower bound of 1.18 here for DAGs with convex cost functions, even with overcharging. And for the case of multicast game, we proved that even with the use of overcharging, we cannot have protocols with price of anarchy better than omega of the square root of n. In conclusion, here you can see a summary of the results that we talked about during the talk. And here are some open problems. One can think about the weighted version of the model in which players have some weights. And another open problem is to think about designing a budget balance protocol for DAGs with convex cost functions. As you may recall, our protocol used overcharging. And another open problem is to think about the gap that we have in the case of DAGs with convex cost functions. We have the lower bound of 1.18, but designing a protocol with constant price of anarchy greater than this value is of some special interest. Thank you for your time, and I would be happy to answer your questions.